Bom dia a todos. Estamos aqui mais uma vez para a apresentação da 10ª EFRAS, mais uma palestra que nós estamos iniciando. E nesse dia a gente está com o professor Christian Boehmer, da Universidade de Londres, na verdade, University College de London. E a sua palestra será sobre as teorias modificadas da gravidade, né? Então, eu agradeço mais uma vez o professor e desejo uma boa apresentação. Good morning to you all. We are here once more for another presentation. And today we are here with Professor Christian Boehmer. And I met him when I visited London. I think his work is very solid, and we all will enjoy his presentation today. And if you have any questions, please make in the comments below, and we'll try our best to answer these questions at the end of presentation. So, Christian, it's a pleasure to have you here, and I wish you a very good presentation.
Okay, thank you very much. So I hope you can still hear me well. It worked a few minutes ago. So good morning, everybody. I've checked the time zone, so it's early in the morning for you. For me, it's the early afternoon. So welcome to this lecture. And for the next hour or so, I will try to give you an overview of modified theories of gravity. And as the title says, it is sort of, I'm talking about the very basic foundations of general relativity, and then how it is changed or can be changed, and then some very specific models that I'm discussing. So let me give you a little outline of the talk. So the first part of the talk is actually very basic. So I'm talking very much about the foundations of general relativity. Things like how many dimensions are we working in and what can we change? And then in the next part, I'm picking up all these little foundations. So all the different assumptions that go into general relativity. And then I sort of investigate them and tell you things that you can change. And then we are moving to sort of the second point here, beyond general relativity. And then I will move on to discuss quite generally models of modified gravity, especially some popular ones that many of you will have heard before, like f of r gravity, f of t gravity, f of q gravity. There's f of a lot of things going on. And then I tell you about some of my more recent work, which I did together with a student, where we are talking about this last point here. So if this still works, yeah, that still works very nicely. So this last point here, linking theories of gravity, this is something that I find of particular interest. So what I'm trying to do is I'm trying to understand how all these different theories that people are proposing, how they're all linked together. And we can actually show that a large family of theories, so theories like f of r gravity, theories like modified teleparallel gravity, and theories based on non-metricity, how they can all be studied in a unified framework. And they're, in a sense, very, very similar. I'll comment on this in a bit. And then towards the very end, I give you sort of some examples of some work that we've done, how you can use these schemes and do some, well, interesting things. But then I find all of this interesting anyway. So let's get started. So the standard formulation of general relativity. So you open a standard textbook on general relativity and you start learning the subject. And eventually you will find more or less the following 6-point mentions. So the first point that you have, which appears from special relativity, is that you're working on a 4-dimensional Lorentzian manifold. So it is called Lorentzian because the signature is not plus, 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 or minus, 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 but there's a change in the signature. So if you look at a Lorentzian manifold and the eigenvalues of the metric, then 1 is negative and 3 are positive in the Lorentzian case. So in the Riemannian case, they all have the same sign. So we are generally working in a 4-dimensional Lorentzian manifold. We assume that there is a metric structure on this manifold, and this metric structure allows us to measure distances. So from a practical physical point of view, it's very important that if you have 2 points, that you can measure the distance between 2 points. Or likewise, if you have 3 points and you connect two relative to each other, then you can define an angle between two lines. So things like this are encoded in the structure, and they're obviously important from a practical point of view, because in the end we want to go into a lab and measure something. The next structure that one introduces on this manifold is the so-called connection, which I here denote with an overbar. And I only do this because my overbar eventually disappears and it means something specific. So we usually introduce a connection or a covariant derivative. And there are different ways how this can be introduced. So probably an elegant way is doing this via a process called parallel transport. And what one does there is one tries to understand how two nearby vectors are connected to each other, hence the word connection, and that naturally gives rise to this gamma, which in standard general relativity is sometimes also called the Levi-Civitas symbol, but I generally call it the connection. And then, so this is where we get a bit more specific. So what one does in general relativity, one assumes that the covariant derivative is metric compatible. So what this means here is that the covariant derivative of the metric tensor vanishes identically everywhere. And the next assumption that one normally does is one assumes that the connection is also torsion-free, or the derivative equally likely. And I tell you what this means. So this means that when you apply two covariant derivatives, or the commutator, and act upon a function, then this gives you 0. So the non-vanishing of this quantity would be proportional to torsion. But in general relativity, this is assumed to be 0. And the final ingredient which goes into general relativity is actually that the action that we write down, which leads to the field equations, is linear in curvature. And this is then the famous Einstein-Hilbert action that I will mention. So let me discuss a little bit what kind of changes we can now make. So let's try to do a little bit more with this mathematics. So the obvious one is, and this is a very early idea going back to the 1920s, is instead of having 4 dimensions, let's just have more dimensions. And the first, or the earliest idea, is probably going back to Kaluza and Klein, who introduced one extra spatial dimension. And the idea that they had was you take the metric tensor and you make it bigger. So you add 1 dimension to it, and the tensor gets bigger, and this gives you 5 additional components. So 4 here, the same 4 here, and then 1 down there in the corner. And the idea was to put the electromagnetic potential, which has 4 components, into these 4 new components, and the scalar field into this 5th place. And while the idea is actually really neat, it didn't quite work as a physical theory, but inspired a lot of other work. I should mention that hypothetically you could increase the number of time dimensions, but this is rarely considered. So I won't discuss this in any way. And there are very few references that you can find. Many unified field theories are based on this idea of just making the structure in a sense bigger. And many other things that are discussed or have been discussed in theoretical physics somehow relate to this theme of more dimensions. So if some of you might have heard twistors, they are related to ideas that Roger Penrose had, and they're usually formulated in a 4 complex dimensional space. So this is an 8 dimensional if you count the number of real dimensions. Then you have bosonic string theory, which ends up being 26 dimensional. And if you have done a string theory course, you might remember you did this calculation where you computed the conformal anomaly. And this simply contains a term that is like d minus 26. So this conformal anomaly disappears when d is 26. And in superstring theory, the number of dimensions sort of gets reduced because the supersymmetry doesn't require you to go up to 26. So more dimensions has really inspired quite a bit of work, but it's only one of the many things that we can do. The next I would like to discuss is playing around more with the geometrical structure instead of the number of dimensions. And the 2 assumptions that we need to discuss here are, why do we assume that the covariant derivative of the metric vanishes? So why do we assume a metric compatible connection? and why do we set torsion to 0? And I'll give you here a little bit of an overview of what has been done. So Cartan, in a sense, introduced the concept of spinors, or became aware of it and started using it, and was thinking about physical applications. And so one can really say that in the 1920s, something like Einstein-Cartan theory started. It was really, I would say, properly formulated and understood more in the 1960s. But the idea is that in general relativity, you have that mass, so the mass of an object gives rise to its gravitational field, and in Einstein-Cartan theory, you get a second set of field equations where the spin acts as the source of the torsional field equations. And the presence of torsion is actually not particularly new at all. So we can trace it back to the 60s, but you can even trace it back to the 1920s, because Einstein himself worked on theories of gravity that were based on what is now called the teleparallel geometry, which actually contains torsion. However, these early theories, they all assume that the metric is compatible with the covariant derivative. And then there was quite a bit of work done in the 60s and 70s. So I mentioned a few names. So Möller was almost more of the 1950s, really. And then Pellegrini, Plebanski, Hayashi, Nakano. They all worked on theories of gravity that were, in a sense, in the teleparallel thinking, where one tries to work in a geometry that uses torsion instead of curvature to model the gravitational field. And this theory that I here denote as GR underscore, and so if I just underline this here, oh, yeah, that's working. So this theory here, GR parallel, so this is often called the teleparallel equivalent of general relativity, and as the name sort of suggests, this theory is indeed equivalent to general relativity. And then if we move forward in time a little bit, so starting from roughly the late 1970s, I would say people then started working on so-called metric affine theories. So these are theories that contain both torsion and non-metricity and curvature. What else can we do? Well, we can change something else, and that is we can do even more. So in general relativity, one can derive the Einstein field equations using the Einstein-Hilbert action, which I've called here as SEH. And what we do with the Einstein-Hilbert action, you integrate the Ricci scalar over the volume. So this guy over here, so square root minus GD for x is the volume 4 form on the manifold. So all we are doing here, you integrate the Ricci scalar over the manifold and you try to find solutions that extremize this action. And interestingly, there are two old papers from one 1970 and one from 1983 that were largely ignored back then because these authors were somehow very much ahead of time. So especially the 1983 paper by Burrow and Ottobel on f of r cosmology, they actually show under which conditions of R a typical cosmological model is stable, which is really interesting. But these papers did not gain much traction. Likewise, so many of you will know this, so Starobinsky was one of the two sort of founders of modern inflation. And he actually found his inflation model by working with a nonlinear Lagrangian. So his action contained the Ricci scalar and then a Ricci scalar squared contribution. And interestingly, while this was hugely influential for inflation, the relativists that could have worked on this were not too interested in these early nonlinear theories that were constructed or that were basically known on this time. And things then changed very dramatically starting from the late 1990s, when all of a sudden we had observational evidence for the presence of dark energy. And this really then kickstarted a huge development in various modified theories of gravity. The early motivation for many of these theories was very much, can we explain the accelerated expansion of the universe without having to introduce a cosmological constant? And then really from the early 2000s onwards, as you can see on the slide there were the early 2000s, you had f of r gravity. Then more or less in 2007, modifications of teleparallel gravity were start to be considered. So that's generally called f of t gravity. And then in 2017, roughly f of q gravity, so q is here the non-metricity scalar, were considered. And f of g gravity, so this is the g here, is not the Gauss-Bonnet term, is another g. Milgram suggested a theory like this, which has very nice links to Mond. And I'll talk about this theory a little bit. And in 2015, we contributed to this by starting to understand how, in particular, f of r gravity and f of t gravity are related. And so what I keep telling students when they talk to me about this field, I usually say sort of from now onwards, we do f of everything theories. Right, so one more item I need to discuss before we are getting more concrete, and this is an item that is sometimes not discussed in a sufficient extent, I believe, and that is in a sense the conservation equation and the equations of motion that appear in general relativity. So it is well known that in GR, you look at the twice contracted Bianchi identities. So the Bianchi identity is an identity of the Riemann curvature tensor. You contract it twice with metrics, and then you can show that the covariant derivative of what we now call the Einstein tensor is covariantly conserved, which then implies that the energy momentum tensor is conserved. And likewise, or it is sort of well known in general relativity that in turn this conservation equation leads or is equivalent to the equation of motion of matter. So that's quite different to electromagnetism. So remember, in electromagnetism, you have your four Maxwell equations. And in addition to the Maxwell equation, you have to be told this is the Lorentz force law. So you have your magnetic field, and if you have a charged particle and the magnetic field lines go up, then it sort of does a circle like this. So it moves to your left using the right-hand rule. And in general relativity, we don't have to do this. So the equations of motion are sort of implied by the theory itself. And this has an interesting point. And the interesting point here is that if you work in any theory beyond general relativity, you should really have a very careful look of what the equations of motion actually are and what the conservation laws are, because in a geometrical theory that models the gravitational field, you cannot postulate specific curves to be, in a sense, the correct curves for your test particles. So you cannot construct a theory and say, I want geodesics to be the curves that test particles follow, or I want these curves or autoparallels or some other curves to be those. You actually need to derive this out of the theory. And it is this final point, I think, that's often ignored when people study modified theories of gravity, because it's a bit of a tricky question to answer what the curves really are. People are very quick to say, it's geodesics. But it doesn't have to be a geodesic. So it's a slight, it's an assumption that you don't have to make, because you can actually derive the correct equations. And moving on from this, so everything I will do from now on will always begin with an action principle. So I always write down an action, which for general relativity is the well-known Einstein-Hilbert action, and then I have some matter couplings. And you see what I'm saying here about my matter couplings. At this point, I assume a minimal coupling procedure, where I take a matter Lagrangian, which is formulated in a Minkowski space, and then I replace the Minkowski line element with an arbitrary metric, and I replace partial derivatives by covariant derivatives. And then I would use the calculus of variations to find the equations of motion. I will discuss non-minimal couplings as well in a little while. So just to set my notation up, R here is the Ricci scalar, G is the determinant of the metric. I have a coupling constant, which is more or less 8 pi. And I have my volume element of the manifold. And my dynamical variables up here in this formulation are the metric and some matter fields. And as I said, so the way I have written down my matter action, or the matter Lagrangian, means immediately this minimal coupling procedure. So what are non-minimal couplings? It's a good question that people like to ask. Well, a non-minimal coupling is any kind of term which directly connects matter fields with geometrical quantities. And all these terms have the property that they are zero if you go to the limit of special relativity. So if your space is flat, these terms all vanish. You see, this doesn't happen up here with minimally coupled terms. So if you were to go back to the flat space formulation, your derivative, well, the Christoffel symbols vanish, but the derivative still becomes a derivative, and here your metric still matches to or gets mapped to some kind of metric. If you think about something like a term here, where a matter field is directly coupled to the Ricci scalar, then you know in the flat space R is zero, so this term is zero. And this applies pretty much to all these non-minimal coupling terms where you couple geometrical quantities to matter fields. This is, of course, a very popular line of research. You can, of course, study a large variety of these coupling terms, and some of them are incredibly difficult to constrain using observations, because all these terms, or the majority of the terms that people study, they usually are only significant when you have large curvature regimes. The other thing I would like to say about these non-minimal coupling terms is that there is really another type of non-minimal coupling term. So you can couple your field to quantities that have a topological meaning, for instance. So a popular theory is, or a popular suggestion was to couple a field, a scalar field, for instance, to the Gauss-Bonnet term, which I here call curly G. And what the Gauss-Bonnet term does in differential geometry, it sort of counts the number of holes in a manifold. So if you have an American donut like this, it has one hole. And if you had two donuts and you glued them together like that, it had two holes. And this Gauss-Bonnet term more or less counts the number of holes in your manifold. But the moment you to couple a scalar field to it, the properties of this term change. So you can check that if you add this Gauss-Bonnet term to the Einstein-Hilbert action, it does not contribute to the field equations because it can be written as a total derivative term. But when you couple it with anything, it doesn't do that anymore. So an arbitrary function of a boundary term, for instance, isn't a boundary term, or a scalar field multiplied with a boundary term is no longer a boundary term. And likewise, and this is interesting for the work I do, is that any term which is a total derivative term, or what I call a boundary term, whether it has a topological interpretation or not is irrelevant, can always be added to the Einstein-Hilbert action, and it will not contribute to the field equations. But if you then couple this boundary term to, again, a field, or you take a function of this boundary term, then you would get contributions to the field equations. And this will become important for what we're going to do. So let me give you a bit of an overview of this large plethora of theories. So the source is given. This is so these figures were done by a few colleagues of mine in a recent long overview paper. And you see a huge variety of theories here. They're all based on non-Riemannian geometries. And what I will do during my talk, I will be able to show you that all these theories here, including those ones, can all be understood together. So I can show you a certain way how you can understand this entire blue box, or blue, it's not a box really, this blue shape, using a very specific unified approach. And likewise, I now show you a second list of modified gravity models. So these are all theories based on Lagrangians, which are not linear in curvature. That's why they're just called higher order theories. And here I can link the previous blue box, or not box, this previous blue shape, I can actually link, for instance, with this. And then in extension with some of the other terms, but I focus very much on this one. So I can link this with that. And I think this is that is a nice result, that you can actually see that you can link these things very nicely. So let's move into this direction of seeing how one can do things like this. So this is just saying what I've said. So I'm creating now a setup where I can deal with a huge amount of theories in one go. And the key equation is really the second equation here. So I'm taking the Einstein-Hilbert action. Here I have now an overbar on top of my R. And that means this is the Ricci scalar constructed on a manifold which contains curvature, torsion, and non-metricity. And it turns out that this scalar decomposes in a very specific way. So this is a formula that you can find, for instance, in an old book by Scout, and it is more or less in there, just not written in this way. And all these terms here have sort of a meaning. So the first two terms, they combine into the standard general relativistic Ricci scalar that is the basis of the usual Einstein-Hilbert action. And then there is a term here, which is called T, which is called the torsion scalar of the teleparallel equivalent of general relativity. And you have here a so-called non-metricity scalar, which has been used for a few years now in so-called symmetric teleparallel theory of gravity. And then you have these terms B, and all these terms B are boundary terms, which means these terms do not directly contribute to the equations of motion. And over here, there is a cross term, and this cross term C is a very specific combination of non-metricity and this S guy, which is sometimes called the superpotential, but it is a linear combination of torsion tensors. As you can see here, you have this torsion scalar, which is quadratic in torsion, and then you can simply force yourself to write it into this form where it's S times T. So S again is linear in T. So you have some torsion non-metricity cross terms that appear here in this term. And it is really this object that we are quite interested in. And why does it help us to understand all of these theories nicely? Well, as I said, what we are doing is we are taking our metric affine action, we have some minimally coupled matter, and we now do variations, if you wish, with respect to the various dynamical variables, which are the matter fields, your metric or tetrad, if you need a tetrad field, torsion and non-metricity. I should just say that, as I said this earlier, the standard source term for torsion is spin 1/2 matter, and the source terms for non-metricity, they're usually called hypermomentum. And I should also say that tetrads are only really needed if one either couples fermions in the theory or if one works in the teleparallel equivalent. Otherwise, in many other formulations, they're not strictly needed. But it makes no difference. This is an equivalent formulation. And I'm just pointing out now the obvious that when non-metricity is set to 0, one finds Einstein-Cartan theory, and when non-metricity and torsion of my theory is completely different, or it has very specific properties unique to that theory. And it was almost said, nobody really said it, but it was sort of the underlying belief, if you read the literature, was that these theories are somehow independent of each other. And the key result of our work is really to show that they're not really all independent. And there's actually an easy way to see this. So a teaser or spoiler is if I write down the field equations of three theories, so f of r gravity, or f of g gravity, f of t gravity, and f of q gravity. So if you look at these three field equations, which are all formulated in different geometrical settings. So line 1, the only geometrical quantity is the metric tensor. There's only curvature. Line 2, you have only torsion. This is a globally flat manifold where the curvature vanishes, and therefore you can map what is in the Levi-Civita part of the curvature onto the torsion, and you end up with a modified teleparallel theory. The third line is a non-metric theory of gravity that geometrically only requires non-metricity to be present, neither torsion nor standard curvature. But if you look at these three equations and imagine you didn't know that these theories were different, you would probably think, oh, someone just redefined a few quantities. So one person called it G, the other one called it T, someone called it Q. And you would think that these theories naively are, well, the same. I shall say they're not the same. But when I saw these equations written out in this way for the first time, I sort of convinced myself that there must be a reason why these equations are so similar. And there must be an underlying reason why these equations, for instance, when applied to cosmology, are actually identical in all three setups. And let me show you how you can understand why this is in fact the case. So first, I discussed a slightly easier result, which is what we derived in 2015. And what we did in 2015 was really, we wanted to understand the relationship between the modified Einstein-Hilbert action and modified teleparallel theories of gravity. And the argument goes as follows. So our key equation is stated here again, which contains all the various scalars, so R, T, Q, and this cross term C, and the two boundary terms. And you see, I haven't split up the R into G and, Q and B, but I'll talk about this later. If we now assume our manifold is globally flat, then we assume, or that is equivalent to saying that R over bar is 0. And if we, in addition to this, set Q0, so if I go into my equation in green here, so if I cross this term out and say it is 0, and then I say this is 0, and then I say this is 0, and remember my term C was a cross term between torsion and non-metricity. So if I switch non-metricity off, this is also 0, and then I'm only left with these three terms here. And if you now go down, these are exactly the three terms that are left. And when you do this, you can simply move the two bits which contain a t to the other side, and you have this very simple identity, namely that the Ricci scalar, the general relativistic Ricci scalar, equals a torsional scalar and a boundary term. And it is this simple equation, as I said, so Einstein has formulated this sometime in the 1920s. So it has been known for almost 100 years now, that this very simple identity can be then used to find an equivalent theory to general relativity. Because if you take this identity here, you can simply put this in the Einstein-Hilbert action, which is the Ricci scalar integrated over the volume of the manifold, and you simply replace it by minus t. Remember, this is a boundary term that in general will not contribute to the equations of motion. And this then gives you the action for teleparallel gravity. But unfortunately, this does not explain the relationship between these modified theories. And now I'm coming back to boundary terms. So remember that if you were to write here f of r, then on the right-hand side, you would want to write something like f of minus t plus b, which is somehow quite different to f of t, because it doesn't differ from f of t by a boundary term, because functions are not necessarily linear. And this means one has to look at this a bit carefully, and the answer becomes actually quite obvious at some point. So some observations are that f of r gravity has fourth order field equations, f of t has only second order field equations, and we have that a linear function gives back general relativity in both these models. And that seems somehow strange, right? Because especially a fourth order theory returning eventually second order field equations, there must be something special happening. And actually what is happening is, or the special thing about this is the boundary term. So it turns out that actually all the higher derivatives that appear in f of r gravity actually can be traced to come from the boundary term that is neglected in the level at the level of general relativity, which is why general relativity is a second order theory and not a fourth order theory. And therefore what we suggested was that actually the correct theory, correct in quotation marks because there's no such thing as a correct theory, but certainly the correct theory to think about is f of TB gravity, so an arbitrary function that depends on the torsion scalar and the boundary term. And what you then get is actually a very nice little figure. And this figure is our result of 2015, namely you have a theory that is an arbitrary function of a torsion scalar and a torsional boundary term. Now, if you insist that within this family of theories you want to work only with second order theories, then you must write down f of t, because you must neglect all the contributions in here that give rise to the higher order derivative terms. Equally, if you insist at this point only that you want a theory that is invariant under local Lorentz transformations, then you must combine T and B in this very specific way, because this is the only linear combination of T and B that is invariant under local Lorentz transformations. And this is, as the identity on the previous slide showed, is exactly f of r gravity. So this means once you start writing down this slightly, let's call this the slightly, maybe almost unnatural combination, but the logical thing. So once you write down an arbitrary function of these two quantities, you actually understand why these two theories are related and how they are related. So one is the second order, the unique second order theory coming out of this function. One is the unique Lorentz invariant theory coming out of this family. And then what is general relativity? Well, it is now perfect sense. So you either go first right and then down, or first you go down and then right. But general relativity is the unique theory that has second order field equations and the theory that is also locally Lorentz invariant. And now we are extending this work a little bit. So the standard Ricci scalar can also be decomposed into a sometimes it's called a bulk term, but into a term that is generally called G and the boundary term. And this G term, again, that what has been known to Einstein, because that term G only is first order in the metric. And because it looks like it's only quadratic and gamma, it looks like naturally like a field strength. And this is quite nice. So if you think about field theories that you want to write down, what do you want to do? You have a potential, you take the gradient of a potential, this becomes your field strength, and then you take the square of the field strength, and this is your Lagrangian. And technically this argument works up to this point. The only problem is that this G, and this is the reason why it's in boldface, it is not a true coordinate scalar. So if you make an arbitrary coordinate transformation, G is not invariant. So G is only a pseudoscalar. It's not a true scalar. And likewise the B. However, the combination G plus B is a true scalar, because the Ricci scalar is a true scalar. And you see now that some similarities with the previous model appear, because previously we had something that was either second order or Lorentz invariant. Here you all of a sudden have things which aren't coordinate scalars. So you will see where this is going. So as I said, the term G also gives rise to the Einstein field equations if you do the variations with respect to G, because this is a boundary term which doesn't contribute. So what does this mean? Well, if you now look into an arbitrary function that depends on G and on B, and you do the calculus of variations and you grind through this procedure, then after, well, a few pages of calculating, you end up with those 3 lines which make up the field equations. The interesting bit is that this first line here is the field equation I showed you previously. The second line contains all the terms that appear if f is also a function of b. So if f does not depend on b, then the last 2 lines disappear. And here on the right-hand side, you have an energy momentum tensor. But you can now ask yourself an interesting question, and that is, okay, here comes some definitions. So if you see here, there's an E here, and this E that appears in the field equations is defined in this specific way. There is a good reason for this. So you have an M here, and this M is the derivative of G with respect to the connection. And if you look at those 3 M's here, this is the same 3 combinations that appear in the Levi-Civita symbol. So you have the index, the plus a cyclic index rotation, and then minus the last of the cyclic rotations. So there is a very good reason why these terms appear. And in these 2 lines, I'm showing you what the Lie derivative of G and B is with respect to an arbitrary vector psi. And these equations show that G and B are not scalars, because if they were true scalars, these second terms here wouldn't appear. And you see again that G is only a pseudoscalar because it depends on second derivatives of these xi's. You can think about those as the generators of your infinitesimal coordinate transformations. So if we now go into this model, I said early on in my talk, we must not assume from first principles that really the energy momentum tensor is conserved. So remember, in general relativity, you have the twice contracted Bianchi identity, and this implies that the energy momentum tensor is conserved. And you also recall that the covariant derivative of t being 0 is not really a true conservation equation in the standard sense, because for that you would always require the partial derivative of something. And if you have the partial derivative of something, you can integrate over a volume, use the divergence theorem, map it to an integral over the surface, and then you can compute your conserved quantity. However, Noether could explain why all this made sense and why one can really speak of a type of conservation equation. So if you follow the Noether procedure all the way through and apply an infinitesimal coordinate transformation at the level of the action, then you can actually show that this action is invariant under infinitesimal coordinate transformations, provided this is 0. So this does not assume that the field equations are true. This is just what comes out of the Noether procedure. And then you can again say, aha, we now know that the covariant derivative of G vanishes, and therefore the Noether procedure implies that this vanishes. For this more complicated theory, things are quite different. And if you do this, so if you work out what is the variation of the action under arbitrary coordinate transformations, you actually find this. Interestingly here, you have this difference between f of g and f of b. So in general relativity, this becomes a 1, I think. And this actually becomes a very strange way of writing the twice contracted Bianchi identities. And there's one reference by Möller going back to the 1950s where he has written them in this very specific way. But it's actually non-trivial to even check that these are the contracted Bianchi identities and that they can be written using only these partial derivatives. The point is that it is actually this equation here that gives us the Noether theorem for our model. So the object in the square bracket has to vanish. But you now see that in this sort of weird looking theory, hypothetically you could have a energy momentum tensor that is non-conserved, and this is somehow compensated by these objects on the other side. But this has, of course, implications for all modified theories of gravity, because this is really the calculation you should do and then check what's happening and not postulating this. So let me now show you how you can relate this theory, for which I've just shown you the field equations, with f of r gravity. And the story is very much analogously to what I've done in modified teleparallel gravity. So what we have here is f of r, again, is a fourth order theory. F of g is a second order theory. All the higher derivative terms sit in the boundary term. And therefore, if we look at an arbitrary function of f of g, this will be fourth order in general. And you see that we have almost a one-to-one correspondence here that is shown in the figure here. And this is a really interesting one. So on the one hand here, on the top left, we have a theory which is based on two coordinate pseudoscalars. So neither g nor b are true scalars. This theory here, the teleparallel setting, is based on two objects. These guys are true scalars, but they are not scalars under local Lorentz transformations. These guys here are invariant under local Lorentz transformations. So you almost have like two dual types of theories. These ones here, they're all Lorentz invariant. These ones are all invariant under coordinate transformations. And here, the only change is that if you want a unique Lorentz invariant theory for modified teleparallel models, you take this specific combination here. Down here, it's a different combination. But the condition is not Lorentz invariance, it is invariance under diffeomorphisms. And now you see how the story will probably evolve. You can now put all of these things together and create a figure which is somehow a convoluted combination of those two figures. So what we can state, and I'm not showing you anything but this nice figure here, we can now say the following. So imagine you started with a very general theory, which depends on a variety of scalars, boundary terms, and a very peculiar cross term, which is the torsion non-metricity cross term. If you put this thing onto a manifold and you assume that this is globally flat, you would end up with something that I would just call F like teleparallel, but really I'm saying flat here, which has all the same arguments except that the flatness condition is taken into account. If you then send non-metricity to 0, you actually end up with modified teleparallel gravity models and TEGR, and if you wish to, theories where your function can depend on torsion and the boundary term. And on the other side here, if you send torsion to 0, you of course end up with theories which are often called the symmetric teleparallel versions of GR, or symmetric teleparallel gravity, which is F of Q. So all these theories, obviously you can also do down here if you wanted to. You could have a third arrow, which would be where Q and that would be here actually. So if you go down here and you switch off curvature and torsion, you would have here F of R gravity, but we suppressed those. We were more interested in these. But you can now see that actually a model of this type naturally connects to F of T gravity, F of Q gravity, and via this route to F of R gravity. So all these models are simply connected because they differ by nonlinear boundary terms. And once you have a nonlinear boundary term, it's simply not a boundary term, and therefore the equations of motion from here to here look generally very different, unless you do special things like cosmology, in which case these boundary terms are always 0, and then their contributions of the field equations disappear, and then you end up with something that looks the same. Right. So this is a quick summary, and then I tell you what one can do with this. And this is sort of a nice little application. So as I said, so F of R gravity, it's invariant under coordinate transformation, invariant under arbitrary diffeomorphisms or coordinate transformation. So somehow you can't break very much. The other three theories I mentioned, you can actually break something. So in F of G gravity, this thing is invariant under local Lorentz transformations, but not invariant under diffeomorphisms in general. So you could break the diffeomorphism invariance. In F of T gravity, you have that the theory is invariant under diffeomorphisms, but not under local Lorentz transformations. You could break them. And in F of Q gravity, it is exactly the same as in F of G. You could break the diffeomorphisms. And one way to do this quite elegantly is the so-called Born-Infeld scheme. So some of you might have seen this used in electromagnetism, where there is a Born-Infeld approach. But the basic idea is, the way I explain this, the following. So if you write down the relativistic Lagrangian for a free particle, then, well, this is it. This is the thing that we know. So you have R dot squared over C squared, and then you sort of play around with it a little bit. And you simply write it in this very specific form, where instead of R dot on the top, you want to write actually the Lagrangian here. In particular, you see the R dot squared in the relativistic Lagrangian actually is related to the Newtonian free particle Lagrangian. So after some redefinitions, you can actually say that your relativistic particle Lagrangian is actually the Newtonian Lagrangian written into this square root-like fashion, and lambda here becomes a certain critical scale. So if you do a Taylor series expansion of this object, assuming that lambda is small, you will see that in first order approximation, it spits out LP and then higher order corrections. Or you just keep it as a finite theory, in which case it is like the relativistic analog. So what the Born-Infeld scheme in a sense says is, if you want to extend it to other models, you say take any Lagrangian L, pop it in here and introduce a new length scale lambda. And this means if you, for instance, apply this to teleparallel theories, you introduce via lambda a length scale, which has units of inverse square length. But the most important thing is that this thing gives you a length scale at which your local Lorentz transformations break. So you introduce sort of an arbitrary length scale, which you generally associate with something very small like that. And this very small scale is the scale at which your local Lorentz transformations will no longer work so well. And you can do something very neat with this model. So you can, for instance, try to study the interior of a black hole in an f of t gravity model using this Born-Infeld scheme. We've done this a few years ago. It all boils down to a single equation, which is very nice. So the Kontowski-Sachs approach is easily understood if you recall the Schwarzschild metric, and then you simply write down the Schwarzschild metric when r is less than 2m, and then you see that the r actually appears in front of all the metric functions, and then you can interpret this as a cosmological model, because when r is less than 2m, the radial and the temporal coordinates, they swap roles. And so it looks like a cosmological model. It looks precisely like a Kontowski-Sachs cosmological model, which is why it's called that. And this is well known. I mean, this has been known even before f of t gravity was born. But what we are doing, we're using this Kontowski-Sachs idea in our teleparallel model. We throw in the Born-Infeld scheme, and what simply happens is that the previously singular center of the Schwarzschild black hole becomes regularized. And the easy way to understand this is to think that what have we done in this theory? We simply introduced a length scale at which your local Lorentz transformations no longer wish to work. And this length scale effectively blows up the singularity. So what was this infinite singularity of radius 0 all of a sudden gets inflated to something of roughly the size 1 over lambda squared. And thereby it becomes more or less a regular surface. So it comes out very nicely. And what I'm showing you here is just the qualitative picture of the solutions of this ODE. So on the left-hand side, you see the relevant general relativistic picture. And what this picture basically tells you is you go onto any of these trajectories on the top, and eventually it drives you to the bottom. So, and if you see where all these curves go, as HA, which is your acceleration, approaches minus infinity, all these curves will eventually end up where A equals 0, which corresponds to the center. So once you are inside the black hole, you will eventually get to the center and you cannot escape it. What is happening in our Born-Infeld type solution is actually really nice. You see that many of these trajectories here are quite similar, but as you approach the center of the black hole, things change massively. So here you see all the trajectories go down, here they all go up. So there is a certain region where you actually get repelled from the center of the black hole, thereby regularizing it. So you can't actually reach it. And what has happened, you get a strange sort of radius that replaces almost the initial singularity, which acts as a focal point for all your infalling geodesics. And yeah, I think I said most of what is on here. So there is this critical radius that is related, unsurprisingly, to our new length scale that we introduce. And we get this kind of strange space that seems to be an attractor for all local geodesics. But the nice thing is we can actually solve the field equations approximately near this radius. And what we found was really surprising to us. Namely, we found a solution that was previously published by Gott in 1985. So that corresponds to to a type of string type situation. And we could then also show that actually our solution is very closely related to the BTZ metric, which you can show by using just the well-known technique of introducing Eddington-Finkelstein type coordinates. So in the Schwarzschild black hole, you use them in order to go through the horizon. And we can actually introduce a very similar set of coordinates near this surface that we find, and again, to understand it. So these are actually really interesting results that come out of this. But what I want to finish with before my summary is some interesting facts about this theory that one can call f of g gravity. So Milgram actually considered that in 2019, and he made this suggestion by looking at some f of q stuff, and he said, well, one could sort of introduce this kind of theory and find a reasonably simple way to realize a Mond type scenario within a modified gravity framework. And what Milgram actually did is he wrote down two conditions. He said that for an arbitrary function to correspond to general relativity for a certain parameter that we can call L, again, that reminds you of the length scale. So if that parameter becomes very large and you want the general relativistic limit, you need your function to be linear in X. And in the deep Mond limit, which you can set where L goes to 0, you would want that your function behaves like the strange root, so 3 to the power over 2. And it turns out, so if we go ever so slightly back to the Born-Infeld scheme, so if you look at this, so this is the standard Born-Infeld scheme here, where you have a square root, and then you have this scale, or the old Lagrangian, and your length scale, but the important thing here is the square root. You can quite easily check, oh, sorry, I went the wrong way. If you look at the conditions that Milgram suggested, you can actually write down a Born-Infeld time approach, and the only difference is instead of a square root, you see, you have here a 3 over power 2, and you can check that this function satisfies in particular these two properties and looks a little bit like a Born-Infeld type scheme, except for the power isn't 1/2, it's 3 over 2. And if any of you are interested in, to the best of my knowledge, this model has not been studied. So a modified gravity model based on this function should contain a deep Mond limit and a general relativistic limit. And for something like f of g gravity, that should also be, you should be able to study this and actually be able to get some analytical results out of this. So let me give you a quick summary of what I've talked about, because I'm pretty much on time. So there are at the moment most certainly too many modified gravities of theory out there, because you can literally do anything and it's too much. And the problem is that if you now look at the different theories that people have formulated, so compare here bosonic string theory in 26 dimensions and teleparallel gravity, I mean, they look like completely different theories. They look like they have nothing to do with each other. You also have these non-minimal couplings, which allow for models that are really complicated. And the moment you go towards non-minimal matter couplings, you can actually write down an uncountably many number of terms. So you can spend your rest of your life just doing this. But it's not necessarily the best thing to do. So one needs to be careful how to choose this. And what I'm trying to say is that it's certainly possible to create a framework where one can study a large amount of these theories under one umbrella. And this is sort of the work I've been doing for quite a few years now. I'm really interested in the question of can one write down some kind of framework or a framework theory that is sufficiently wide so that all these theories fit together under this one framework. And the long-term hope would be that if you're able to do this, so if you can write down a theory that is maybe very complicated, but so general that it contains all the other theories, that then if you're able to constrain this one theory even if it's slightly more work than the other ones would be. But if you can find a constraint for this one, then this constraint will obviously propagate to all the other modified theories, and you would be able to then have a constraint that hopefully will rule out a lot of these theories. But that is a difficult one to achieve. That's quite a challenge. So thank you very much for attending this lecture today. I'm giving you 3 references here. The first one is the most comprehensive one. So this is quite a lengthy paper, and this is where we discuss a lot of the details of the relationship between the many different theories. So thank you very much. And if you have any questions, I'd be more than happy trying to answer them.
Thank you. Well,
Thanks.
Thank you, Professor Boehmer,
you.
for this very good presentation. And Eduardo, do we have questions? Yeah. Okay. Let me see here. Just one. Let me see here. Well, we have a question here from João Paulo Moraes. I'll quote exactly the question. If I understand correctly, even for GR, you split the action in a bulk and a boundary term. Do you think this can be used somehow for holography?
Oh, wow.
Once you have a boundary
Yes.
term?
I mean, I've never looked into these holographic things or into ADS CFT or so, but so yes, you certainly have a boundary term, but it's a tricky one. I don't know. To be honest, I'm sorry, I can't answer it well. It's a very sort of, the question is great, but I don't know how to answer it nicely. But you definitely can split into a bulk and a boundary term. Yeah.
Yeah.
Sorry.
And I have another question. Speaking of boundary terms, do you believe that f of t theory can be made invariant under local Lorentz symmetry
Yes,
just by
this is
adding this boundary term?
So, okay, so if you ask the question like this, then the answer is, strictly speaking, yes. So if you choose a correct f, so if you start with f of tb, then you can find theories which are invariant under local Lorentz transformations, which is simply you do minus t plus b. So the secondary question, and I know what you want to know about this, the secondary question is, if you just have f of t gravity, can you make choices at some point during this process that reinstates the covariance of the theory by choosing your connection wisely? So I know that many of my colleagues believe that this is the case. I haven't seen it in my framework yet. Because the problem is that the moment, so let's put it like this, I think everybody can agree on the following fact. If you set the spin connection to 0, you have made a choice. And once you've made this choice and then you make a local Lorentz transformation, you will break this choice. There's no discussion about this. Everybody agrees with this, I think. Whether you can subsequently fix this by a very clever choice, I haven't looked into this for a while. But I know that a lot of my colleagues are convinced this to be the case. But I also know that many people are not happy with this idea.
I see.
So
Very good. So we don't have more questions. I told you 30 minutes would be
too much for questions.
too much
Yes.
for questions. Well, so I thank you again, Christian, for this very nice presentation and for your time. I know it's these days it's very, valuable asset. So thank you very much.
No, thank you very much for the invitation. It's my pleasure.
Oi.
Yes.
Another question. You can read that. Yeah, you did you send me? Você me mandou a pergunta? Just a minute.
It's okay.
Vamos ver. We have a question here from Vitor Mesquita. In some space that have homeomorphism, this generalization become more simple?
Homeomorphisms.
Yeah, I'm not sure what he's talking about, homeomorphism.
Yeah, I know what a homeomorphism is. Maybe we can ask the person who asked the question to maybe ask it slightly differently.
Yeah, Vito, maybe you can ask in another way. I'm not sure, because let me write again. In some space that have homeomorphism, this generalization become more simple. Well, generalization of f of t, b, q theories.
So, I mean, one thing which I said in the talk, and this is slightly related to, hopefully slightly related to the question is, so if you look at cosmology and you have a flared Friedmann, Lemaitre, Robertson, Walker space-time, it turns out that the equations for f of q, f of t, and f of g are identical. And we can show why this is the case. So yeah, things become simpler when spaces have many symmetries, but our approach allows us to actually track why this is the case. What you can actually show is that the boundary terms, all of them, identically vanish in cosmology. And also, I mean, this doesn't mean they contribute to the field equations, but you can also show that none of them contribute to the field equations. And so therefore in cosmology, the equations are the same. And you can find like 100 papers where the author writes, oh, surprisingly, the equations are the same as in the other theory. But nobody's sat down and said, well, if the equations are the same, there must be a reason for it. That's not an accident. So
Yeah. Let me see for another question. Well, again, João Paulo, I mean, said just one more question, but we have no question here. He said you cited an old book in GR. So I don't know if he want to know what exactly the book, or
he might. There's one book I mentioned, which was the book which is called Ritchie Calculus by Schouten.
Rich Calculus.
Yes, by Schouten. It's available. Springer has reissued the book, and they also sell the PDF file now. And this book contains, in particular, let me scroll back to this. So our key equation that is sort of at the basis for everything. This one where I crossed out some terms. So this equation is pretty much in the Schouten book. So it's in section 3 called linear connections, and the fourth subsection in this section is, I think, called identities of the Riemann tensor, and that contains this part. So it's a well-known book and a well-known formula, but very few people have actually written it in this very specific way. So especially this cross term, nobody has spotted that you can actually write this with a superpotential and contract with Q, and that comes out. That is a very sort of neat way to write it. So I think it was probably this book that was mentioned and that the person wants to know. So Ritchie Calculus by Schouten.
Okay. So Vitor Mesquita said, sorry, the generalization is the theory that unificates the modified theories of gravity.
Can you say that once more, please?
The generalization is the theory that unificates the modified theories of gravity.
Yes, absolutely. So this big generalization that we have written down. So this complicated
his
thing.
question is, in some space that homeomorphism, this generalization become more simple. I think he wants to know that homeomorphism will turn the generalization more simple.
I don't know quite how to answer that.
Yeah, I think this is really quite simple.
Yeah.
Because it's already simple. I mean, the whole idea of generalization is to make that simple.
Yes. So the idea is, yeah, I mean, so the situation we've had so far was that people were working in theories and they all claimed that their theories were sort of different and that they were also unrelated. And neither is quite true. So the point is, when you actually look at the mother theory of this, there is one. And this contains really everything. And actually in this setting, to answer your question again, so in this setting, you could actually ask, what happens to this action under arbitrary Lorentz transformations? And you will probably find an equation that is similar to a conservation type equation. And then you can make a choice of how you want to solve this. But this is actually a calculation we hadn't done because the paper was almost 30 pages long when we got to it. So,
Yeah.
We had to choose, we had to sort of put the focus somewhere, and we just didn't do this. But I think that is a very something we can do.
Yeah, maybe I think people want to know, are there another hidden symmetries inside this model? I mean,
Yeah, I mean, the question is, how far do you need to generalize? So we are not aware of sort of hidden symmetries, but there may be some there. So I can't tell you that there aren't. This is actually quite an interesting point. So I haven't included this in the talk, but so during the calculations that we have done, so some of these, we had a conjecture, and our conjecture was that one of the boundary terms we found was actually another boundary term that was well known. But the conjecture was false. So we tried this for 2 weeks, and what happened in the end that we realized the terms were different. So, and what happened was, and this is the interesting bit, that the two boundary terms differed by another boundary term. That's by default, right? It can't be a non-boundary term. But it turns out that we found a boundary term which had very strange properties. It was not a coordinate scalar, and it was not a Lorentz scalar. So somehow this thing could sense how well you chose your coordinates and how well you chose your frames, and it sort of understood the relationship between the two. It's a very strange term, but it is a boundary term that in itself does not contribute to equations of motion. But this term might well be helpful in understanding what's going on with these theories. So we found some terms that actually they're easy to write down. You would never guess them because they're just weird. But they have very unusual properties, and we actually don't know the meaning for them. So you have heard in f of t gravity, you have this thing called the Remnant Group. So there is even an idea, I mean, it's just a pure idea that one should maybe check that these boundary terms might not help in understanding that Remnant Group, because these terms understand both. You see, they understand the coordinates and they understand the Lorentz transformations.
yeah, and did you take a look at the invariance of this Remnant group?
Well, what we could check, I mean, not generally, but what we could check, that for sort of good coordinates or good tetrads, these terms tended to be 0.
I see, the old problem of good tetrads.
Yeah, so the good tetrads always gave zeros, the good coordinates gave zeros, and some combinations gave zeros. But you see, it's not enough to say something more concrete, because it's very easy to say under these conditions the term is zero. But if you want to go backwards and say, okay, what are the conditions under which it is zero, you end up with the very, very protracted set of equations that you can't sort of handle.
I see.
But yeah, these terms are really interesting.
Let me see if we have more questions here. Well, no. Yeah, apparently, okay. We don't have questions, any more questions, so thank you very much.
Thank
And
you for
Eduardo,
inviting me over.
have a
Let me
nice
stop
day, and
share. Yeah, thank you
we
very
hope
much.
we met again.
Yeah, and I hope your school will carry on going well.
Yeah.
Okay. Thank you.
Bye.
Bye. Bye.
Fechou aí, Eduardo?